Good morning, good afternoon, and welcome wherever you guys may be watching from. Thank you for joining us today for our Vaughan webinar on giving your digester an organic diet, keys to a successful co-digestion program. I'm your host today. I'm Stephanie Vaughan. I'm the marketing director at Vaughan Company. And again, pleased to welcome you all with us today. And to those who will be watching on demand in the future, thank you for joining us for that as well. We received registrations from people located worldwide, which is very, very exciting to my presenter over here, Erik Larson. This is something that he's very passionate about and is really looking forward to sharing this topic and information with you today. Real quick on the Zoom platform that we will be using today or that you're currently on, that chat box, please use the chat box for chat only. We will be taking questions from the Q&A pod only. So please place any questions that you have and that you would like Erik or any of our other, Steve Macomber, who will be joining us as well, to take those questions. There will be poll questions sprinkled throughout today's presentation. Please join us in answering those. We would love your feedback and the answers to those poll questions. And without further ado, we're going to send it over to Steve Macomber over in North Carolina, coming to you live. So let's get started this morning, guys.
Hello, everyone. Good morning. It's like I don't have video at the moment, but those of you who know me know what I look like. Those of you who don't, I will hope to see you at WEFTech. Very excited to be here. Thanks for joining us for what is sure to be a very productive conversation about giving your digester a nice, healthy, organic diet. This is another one of our series of webinars. We have many others, so I'd like to ask everyone to check them out at chopperpumps.com. These have sort of gone in order in a series as questions come up over the last year and a half or so. We've added webinars based on feedback, and we will continue to do that. Again, my name is Steve, and before we jump right into the technical presentation from Erik, the engineers are known to do, we like to jump right in. I'm just going to go over a few other housekeeping items. I like to also set the table, pun intended, with a little background on Vaughan Company. For those of you who don't know us yet. So Stephanie already mentioned that chat is for chat and Q&A. You have to answer the poll questions. We do ask that you do that in the Q&A section of Zoom. So yeah, even after a year and a half, there could be technical glitches, as all of you know. So please bear with us, and please make sure you look for us in person at WEFTech. We look forward to seeing you there. So with this co-digestion, we're talking about diverting all different types of organic material away from landfills. And with legal requirements and economic opportunities, this topic is only going to get more important in the coming years. And I'm going to go to a slide here shortly and give you a little bit of background on Vaughan. Here we go. So those of you who don't know, just briefly, Vaughan's a fourth generation family-owned company. Began in a weld shop next to a gas station in rural Washington state, helping dairy farmers with pumps that were clogging for various reasons with feed, hay, wire. And the thought was, Jim Vaughan, there must be a better way to do this. First patent issued in the late 50s, and we have continued to make iterative improvements over the years. We don't rest. We're always looking for new ways to do things. 30 different international patents. We're global, products throughout the world, 35,000 units, and with our mixing system, well over 2,500 installations of our Rotamix system. So chances are, if you have an application, we've done it and have some feedback to help support your efforts. So this is the last slide I have. I wanted to mention that we do have $5 to $7 million worth of spare parts, which is no small feat, very important in terms of getting parts that you need. If something, mechanical pieces of equipment at some point will need maintenance, will need to be repaired. It's a guarantee. It's not a what if. So we're there for you. We like to expedite if necessary. We do have something called a try and buy program. If you're not sure, something that we have, ask us about that. We have install lists available upon request. And of course, everything we have is made in the USA. And we're going to have a chance for more contact information at the end of this presentation. But I'd like to hand things over, the little introduction, to our senior engineer, Erik Larson. Erik's a professional engineer, registered, I know, in Washington State and possibly somewhere else. Erik, I'm sure he'll tell you. He's also a member of the WEF Biosolids Committee, just to name a few of his accomplishments. Erik, are you ready to go?
Yes, I am. I think you can hear me. Welcome, everybody. Nice to have you today. It seems like we had a little bit under 300 people signed up, and so hopefully everybody's in there and we're ready to get going today. My name is Erik Larson. I'm a senior process engineer here at Vaughan Company. I've been with the company for a little over 8 years now. And as Steve mentioned, I'm licensed in the state of Washington. I'm also licensed in North Carolina and Georgia, of all the random places, but very happy to work in all the states I get a chance to work in, and especially internationally as well. This is a topic that's near and dear to my heart. I think it's an important topic as we move forward, talking about renewable energy, talking about landfill diversion, renewable use of biosolids and nutrient recovery and all of those great topics. So looking forward to speaking to you about those issues today. With that, I think we'll go to the first of my slides. So today we're going to cover a couple different topics. First, we're going to cover the what's and whys of co-digestion, then sourcing, receiving, and feeding of biosolids, maintaining a balanced diet. So we're going to talk about fog, sugars, and protein and how those come into a balance to maintain a biomass for your digester, and then the importance of a proactive digester management program. So what is co-digestion? Co-digestion is a simultaneous anaerobic digestion of multiple organic wastes in one digester. So anytime that you're mixing different feedstocks, you're mixing different organic waste streams into an anaerobic digester, you're doing co-digestion from a technical standpoint. So why co-digest? You want to co-digestion for improved biogas production. Co-digestion increases biogas potential by increasing organic loading rate to the digester, which provides for higher gas potential. And then fog especially has been colloquially called the jet fuel for digesters. So in a lot of cases, and especially initially, a lot of facilities have been adding fog to their digester to produce more gas and to increase their gas production capacity, especially when looking at cogeneration. In some cases, co-digestion can help balance digesters that may see inhibition without augmenting organic loading, allowing for more stable digestion. There are certain cases where you might have a very low organic yield or might have other issues with the main waste stream going into the digester and may need to look to augment that. And those applications will also be considered co-digestion. Regulatory requirements. So landfill diversion of organic material. This is an important policy goal in many states and regions and is driving a lot of co-digestion where anaerobic digesters are seen as one of the potential areas where organic waste going to landfills can be diverted to, where composting is sort of the other main one, and there's a few other different technologies, but those are the two main ones. Anaerobic digestion is a major receiver of these diverted organics, as I just mentioned, and these waste streams can be diverse, including fog, food waste, processing waste from manufacturing and agriculture, manure and silage from agricultural facilities as well. All right, global food waste management market expected to grow 5 to 6% per year between 2001 and 2028, from $36 billion to $56 billion. That's in US dollars. Food waste per capita can be estimated at approximately 6.5 to 7.4 wet pounds per person per week, which is quite a lot of waste production when you look to scale that out to the entire population. So sourcing organics. For some, sourcing organics can be profitable. For others, it can be a continuous challenge. And we've seen this across the various projects that we've worked with in the US. Diversion programs can provide a steady supply of consistent organic load. A lot of these are generally done on a contractual basis where there'll be a policy-driven diversion program that looks to target certain sectors of the waste generating economy, whether that's, for example, in New York, they have a school food waste diversion program that delivers a very fixed amount of food waste into the digestion program at Newtown Creek and other facilities. And then it could be an agreement with a manufacturer or some sort of waste stream producer diverting a very specific type of waste like brewer's waste or with a brewing market, or it might be some sort of manufacturing confectioner's waste or some other stream. But generally, these are going to be fairly steady, contracted. There'll be, so many tons per week or so many tons per day, looking at these on a contractual basis and generally run pretty steady. The other side of the coin is septage and high strength waste receiving, which are generally the least stable. And these are going to be kind of your tipping fee situation where you're receiving, restaurant grease from haulers, you're receiving, and in fact, that could actually be something that is fairly stable if it's on a contracted basis and you're receiving that from a very large market area. But generally, if you're receiving it on a tipping fee basis, they're going to bring it to you whenever they have it, and you're going to have to take it whenever they give it to you. And that can provide for some very challenging operational constraints when you've got such a diverse receiving program that's collecting various different things at different strengths and different organic loads that you have to maintain and find a way to manage in a digestion process. There we go. Balance of contracted. So a balance of contracted and uncontracted sourcing can provide better economics while reducing volatility. So from a receiving strategy standpoint, you want to receive different types of waste separately whenever possible. If you're receiving fog, receive that into a fog receiving tank that's specifically set up for that. If you're getting food waste, if you're having to do depackaging or something else, set up a separate receiving train for that. Have separate tanks and mills and whatever you need to receive that product, but set that up in different trains. Don't try to collect everything in one pit and then send it, and don't collect it directly into the digester either. I've seen that where they'll have a quick disconnect port on the digester with a valve, and they'll just bring trucks in, hook them directly up to the digester and dump it in. You absolutely can get away with that, but I think it's a recipe for disaster as far as someday you're going to receive something that's going to not get caught until it's already in the digester, and then it's too late. So developing a testing strategy to determine organic strength and screen for inhibitive loads. You want to understand what's going in, what you're receiving, what the organic load strength is of that. What is the, chemical oxygen demand? What is the pH? What is what are all the different characteristics of that waste so that you understand what you're receiving and how it's going to interact with your digestion program. And then you also want to screen for inhibitive loads. You don't want to be putting in things to your digester that are going to cause problems. We had a little joke putting this together about, if you've got somebody that's bringing you food waste and they bring you 2 tons of lemons, you might not want to add 2 tons of lemons to your digester. So if someone's trying to give you lemons, maybe send them to the landfill. Because the pH of that's going to cause some serious issues for you if you're not prepared to handle that without any other anything else to add to that. And then put an option to turn away hazardous organics in your contract. So you always should do the best you can to reserve the right to turn away something that's going to cause a problem for your digestion program. A lot of these programs are landfill diversion, and some things can't be diverted. And so if you are receiving things that have toxic elements to them, heavy metals, things that are going to cause problems for your digestion program, whether it's the biosolids you're producing, the health of the biomass within your digester, you should always reserve the right to refuse service whenever possible to help deal with that. And then use blend tanks to provide homogeneous, stable feed to the digester. So you want to receive everything separately and then bring it into a blend tank, blend it, and then use that as your process to feed into the digester. Use that as your equalization of your feedstocks into the digester so you can provide a stable feed to your digester and maintain a good balance in your digestion process. So here's a few examples of different receiving tanks and a few projects that we've worked on. The one on the right is some fog receiving tanks that I believe were funded by Chevron, looking at fat, oil, and grease diversion. And then the one at the left is a renewable energy biogas production facility. And these are the receiving tanks from the trucks that would bring organic waste in their facility. So you can see multiple tanks, small tanks, a couple transfer pumps. If you're looking at seriously getting into co-digestion, or you have a customer that's interested in getting into it, the more work you can do on the front end to provide them flexibility in their operation, or the more you can do to provide flexibility in your own operation, the better off you're going to be and the more stable your operation is going to be, because you're going to have control. And I think that's the main key to having a stable digestion program, especially with co-digestion, is to maintain control of the process and be proactive and not reactive. So feeding strategy. Maintain balanced feed rates to the digester. Don't dump an entire truck of fog out of nowhere. There's a whole lot of reasons why you don't want to do that, but any spike loading that you're going to provide to your digester is going to create imbalances. And we'll talk about that. We'll talk about why in just a minute. Feed small amounts often, and continuous feed is the best if possible. And in some cases, you might not have the personnel or the controls to provide for continuous feed. You may not even have the organic load or the volume to do that from the standpoint of pump capacities and things like that. But whenever possible, a continuous feed to a digester is going to be the best strategy. I know that there is a mentality about feeding and decanting, and there's definitely a place for that. But you have to remember that the majority of digesters are continuously stirred tank reactors, and we should be operating those like in that configuration if that's how they're designed to operate. I would say 95% of digesters in the US at least are continuous stirred tank reactors, which means you should be continuously stirred. You're mixing all the time. You're maintaining homogeneous volume, which is going to be best for your biomass and your gas production. But it also means you can't really decant. You shouldn't be separating out your digester contents, and trying to operate in that is going to hurt your gas production, hurt the stability. So just something to keep in mind. Use metering and blending to control the addition of high strength waste and spread them out over time. So if you do get an entire truck of fog, sorry, we've got a train going by. If you've got an entire truck of fog coming in, have a fog receiving station, have the ability to meet that in the digester and send it in the digester slowly over time. Spread that out as much as you can, and try to maintain the same level of feed to the digester so that the digester gets used to seeing that fog coming in at a steady rate, and your biomass can adjust to address that and provide for the best gas production and anaerobic activity. And then don't be afraid to augment your feed if needed. There's nothing wrong with having either chemicals or just alternative feeds that you're maintaining for this purpose. I know a lot of facilities that do food waste that have the ability to call in for manure whenever they need it to help adjust and augment that process to add some nitrogen and to provide some alkalinity. Don't be afraid to add carbon if you're receiving a lot of protein waste and your nitrogen's pretty high and you need to add some carbon. Silage. So like if you're doing a manure digester, a lot of times you'll add silage, which is the straw and the plant waste, which is very high in carbon. It'll help balance out that carbon nitrogen ratio. So don't be afraid to augment. Don't feel stuck. Have some chemical augmentation, bicarb, things like that, or whatever you're using for pH adjustment. Have some stable feed sources that you have in the side. You can have them in holding bays or silos, and have that so you can add it whenever it's needed to maintain a balance when the organic load that you're getting in from your sourcing is not really cutting the mustard.
All right, we're going to pause for just a moment here, and we are going to introduce a poll question. It says number 2, so I apologize. So we're going to start with which of these digesters would be considered co-digestion. Your choices are municipal digester, which receives septage from haulers, manure digester on a farm, which receives silage, private biogas digester, which receives food waste, and fog. Remember, your participation is much appreciated. You guys are a smart bunch. All right, it looks like, there you go. 75 of 162 of you are participating. Keep those answers rolling in.
Great answers.
All right, we'll give you just a few more seconds, you guys.
just as a note, for those of you that are looking to get development hours or continuing education credits for this, your participation in the poll is going to be important, depending on your regulatory body, for us to show participation in providing you with accreditation for the hour. All right. So for those of you that are wondering, the answer was all of the above. All of those different examples are performing co-digestion. They're receiving a main waste and then also receiving a secondary waste stream that's either providing balance or just two different streams coming together for the anaerobic digestion process. And so that kind of segues us into the anaerobic digestion process. So I want to do a little bit deeper dive into what's going on in an anaerobic digester. And for those of you that have joined previous webinars, we've done these a few slides before, but I want to talk about a few specific things as they relate to co-digestion. So what is anaerobic digestion? It's a series of biological processes in which microorganisms break down biodegradable material into methane, CO2, and energy in an anaerobic environment. So looking at the anaerobic digestion process, this is a great chart. The percentages are not necessarily representative of what you'll see in a standard digester, but are just there to show how everything moves between these different components as it works its way into the methagenesis and the methane production. And this excludes, the CO2 production, but it's still there. It's just not on this chart. So you've got your hydrolysis step. This is your disintegration and your hydrolysis. This is taking whatever that organic waste is and breaking it down into its constituents. So your monosaccharides, your amino acids, and your long chain fatty acids. And as you can see, those are pretty directly down from your carbohydrates, your proteins, and your lipids. And since hydrolysis is the rate limiting step, that's going to have a lot of implications on the timing of gas production, how the organic loads that you're sending in are reacting, and how much gas potential and methane potential you have. So you can see your carbohydrates are going to break down completely into monosaccharides, your proteins completely into amino acids, and your lipids are going to break down into long chain fatty acids with the glycerin, which I think is being listed as a sugar here. But you can see how that breaks down. Next, you have the acid phase. This is your acetogenesis and your acetogenesis. And these are two distinct steps that have different biomasses that provide these different steps. So breaking down your monosaccharides, your amino acids into your organic acids, and then your long chain fatty acids are actually going to break down directly into acetic acid. And all of these processes are going to produce free hydrogen from the production of acids and the freeing of that hydrogen ion. And then you've got the acetogenesis phase, which is where all of those organic acids get converted into acetic acid, which is the main precursor for your methogens that they intake and then put out your methane. And then the methane phase, which is just the conversion of all the acetic acid and all of your hydrogen into methane. And there's some stoichiometric constraints on how much methane you can produce. And you actually can look at how much leftover hydrogen you have in your gas headspace and your CO2 contribution. You can kind of back calculate to see if you're seeing the expected gas production, but we're not going to get into that in this presentation. But there's a lot. There's a very layered, deep dive you can do into gas production metrics to better understand how your digester is converting all of the organic load you're putting into gas, and what biomass is maintaining and controlling that process. So up here you've got your solid, your liquid, and your gas. I like to just provide this to kind of give an understanding of, before disintegration, before hydrolysis, everything is kind of solids floating in the soup. And as you break it down to these acids, they become soluble and move into that liquid phase. And then those get uptaken by your methogens and produced into gas, and the gas will bubble up into the headspace. So a balanced diet: fog, sugars, and proteins. We're going to deep dive into these three. So fog is going to be, greater than 90% volatile solids, 95, 96, 98, depends on how pure the fog you're receiving is and how much contaminant there is in it. Very, very high methane potential. And I think the key here is it quickly hydrolyzes in the digester. We're talking about less than a day. So, for those of you that have operated digesters that have received fog, you'll know if you feed a lot of fog in your digester, you're going to see that within 6 hours on your gas production, on your gas log. And I think that's what I want. If you take away anything from the fog slide, I think that's what I want you to take away is the reason why fog is called the jet fuel of digesters is because of this very quick hydrolyzation time. There's not a lot of lag between adding the fog to the digester and seeing that fog producing gas, because that breakdown of fog, especially if it's restaurant grease or already processed oil, you're going to be breaking that down directly into those long chain fatty acids, and that's going to be converted directly into acetic acid. So you've got very few steps and a very quick, metabolized process that's going to hydrolyze that, turn it into the constituents needed to make that methane. But the other issue is this can cause your VFAs to spike. So your volatile fatty acids, when you add fog, you're going to get a very quick conversion into volatile fatty acid, and that's going to cause your volatile acid levels to spike. And this can contribute a lot to foaming issues, because the high volatile acid is going to drop your pH slightly. It's going to provide good conditions for foaming to happen. And we cover that in a little bit more depth in a previous webinar we've done on foaming. So sugars, these are going to be your carbohydrates. I would say the majority of, if you're receiving food waste or various other things, sugars are pretty strong organic building block. I would say the majority of what you're going to receive besides fog is going to be sugars. And these are going to be from many different sources at many different strengths. There's a large variability in volatile solids and methane potential, but pure sugar acts very much like fog. It is refined. It's going to very readily hydrolyze. You're going to have very, very high methane potential. The organic component of that's going to be greater than 90%, up to 100%. But the key here is that processed sugars may hydrolyze in hours, but cellulose and other complex sugars are going to take days, because in a lot of those cases, it's going to take enzymes, it's going to take specialized biomass that is able to attack those complex sugar networks. And things like lignin, which is technically a sugar, you're probably not going to be able to break down at all. It's probably just going to act almost like an inert in your digester. So don't take waste from mushroom farms, I guess, would be the takeaway there. But processed sugars, they're going to be like jet fuel as well. If you're getting confectioner's waste from a candy manufacturer, which I've seen projects that received a steady supply of that, it's going to act just like fog in the sense that you're going to see some great methane production, and you're going to have the same sort of operational challenges that you might have if you're receiving purely fog to augment your digestion process. But food waste, food sugars, fruits, things like that, cellulose waste from vegetables and other organics, those are going to take a little bit longer, 2 to 3 days to actually hydrolyze and start to break down and get into the same place that these refined sugars are already at. And again, the majority of your organic loading is going to fall into this category for the most part. Proteins, these are complex organic molecules. If anybody's ever seen, those protein images with they're folded on top of each other and folded and folded and folded. Proteins are very complex molecules. And because of that, they have somewhat poor methane potential. Not all of the protein molecule is going to break down into amino acids and components that are going to directly convert into methane production. Very slow to hydrolyze. Again, you've got the enzymatic action. You've got to break down these proteins, denature them, break them down into their amino acid components, and that can take some time. And then they're generally going to be nitrogen rich. And really, this is going to be one of your only sources of nitrogen. There isn't going to be any nitrogen loading from your fog or your carbohydrates. It's mainly going to come from proteins and other sources. And so when you're trying to balance your carbon to nitrogen ratio, you're going to have to look for nitrogen if you're receiving only fog to maintain a good ratio there. Manure and silage. Relatively low methane potential. I would mainly look at these two as augmentation. These are fairly easy to source and great for augmenting your feed rates. They kind of bulk up your feed rate, can help kind of cut. It's kind of like you're cutting the purity to some extent of trying to maintain stability and keep a steady feed rate by using manure and silage to kind of balance your carbon nitrogen ratio, balance your add alkalinity if you're not getting a lot of alkalinity and you're adding a lot of acidic, food waste, fruits and things like that are going to have a pretty low pH. There's a lot of good things that can come from adding manure and silage, even though they don't have the greatest methane potential as compared to the other sources we talked about. And silage is going to provide you carbon, which is always a good thing if you're on the other end of the spectrum and you're not getting a lot of carbon into your digester and you're receiving a lot of difficult to digest waste, and you need to provide that carbon to help balance out the process. So meal planning, test and balance incoming feedstocks. Understand what you're receiving and have good programs to look for pH, TKN, total nitrogen, volatile solids, total solids, alkalinity. Understand all of these different factors about what's coming in, and do an inhibitive assay. Understand if there's any inhibitive substances or any inhibitive potential in the incoming feed, and try to either turn that away or understand that this is going to be a problem and find a way to balance that out and minimize the impact. Providing a consistent organic loading rate. So don't just look at pounds that you're adding to the digester. You want to look at the organic load that you're providing to the digester. So just because you're providing the same pounds per day into the digester doesn't mean you're providing the same methane potential or the same organic load in the digester. This is where blending really becomes key, where you can take all these different constituents, set up a feed schedule into your blend tank, and then your blend tank is providing a very stable feed that may be able to be averaged over the course of a day rather than being point sources going into the digester. And then provide a consistent carbon to nitrogen ratio. Again, these are all things that are looking to balance the load into and maintain a stable load into your biomass, because your biomass is going to be selective for the conditions in the digester. And so if you're constantly varying those conditions, you're never going to allow one biomass to take over and provide for the highest methane production and biomass production rates. So important targets, pH of 7 to 8. I know there's a lot of discussion about 6.5 to 7.5. And I think if anything, 7 to 7.5. Once you get below a pH of 7, your methogens are going to be inhibited. And if you get below 6, they'll stop functioning altogether. But once you get below 7, you're going to start inhibiting your methogens, which is going to cause your volatile acids to start to build up, because the bottleneck then becomes the conversion from volatile acid and into methane. And so maintaining a pH above 7 is going to be really important, especially if you're receiving a lot of high acid food waste, to make sure that you're maintaining your methane phase and not inhibiting it. Now, once you get above 8, you start to have other issues. So I think staying in the low 7s is probably the best bet, but I really wouldn't recommend operating at 6.8 or 6.7 if you can avoid it. So your volatile acid alkalinity ratio, this is a good proactive thing. You want to keep this below 0.1. I know I've seen below 0.35 as being something that seems to be pervasive in the literature, but once you get to 0.35, you're really past the point of no return. If your volatile acid alkalinity ratio is 0.35, either your alkalinity is way too low or your volatile acids are way too high. And either one of those are going to create runaway problems that are going to lead to a pH drop in your digester without immediate intervention with bicarb or other alkalinity. And you're going to see the digester basically die. You're going to see your pH drop below 6.5, below 6. You're going to have just a total kill of your digester if you get up to 0.35. So really, you want to be below 0.1. If you're above 0.1, you should be taking proactive measures to get back below 0.1, whether it's adding alkalinity or maybe limiting feeds that you know are going to produce a lot of volatile acid production, at least in the short term, so you can build back up that alkalinity and maintain stability. You want your volatile acid levels to be between 50 and 300. And the reality is if you're doing co-digestion, you're probably going to be near the higher end of this. You're going to be in the 240s to 250s. And really, as long as you have strong alkalinity, up to 500 can still be managed, but it's going to be a lot more, difficult and a lot more potential for upset. So, try to be below that 300 level. Alkalinity, especially if you're co-digesting, you want to be 2,500 to 5,000. I know there's in literature, you'll see 1,500, and that's totally fine for a conventional digester. But if you're co-digesting and you're getting fog or food waste, you want to maintain that higher alkalinity so you can provide that buffer. It's not going to cause any problems for your digester. And it's just a more stable place to acquiesce your digester at than at the lower ends of alkalinity, where you might have issues if you've got strong volatile acid production. Carbon nitrogen ratio targets 20 to 30. If you're doing thermophilic digestion, you can go a little higher. 30 to 40 I've seen recommended. This is something that I'm really basing a lot of my data off of what's being put out there by the EPA and other sources, at the AgStar program for manure digesters. But everything I'm seeing is showing 20 to 30 carbon and nitrogen is going to be your best bet for mesophilic. 30 to 40 is going to be your best bet for thermophilic. And, your mileage may vary, but I think find what works and stick to it. So this is a good initial target, but whatever that ratio is, try to maintain it stable because it's going to impact your biomass. And then ammonia concentration below 2,500 milligrams per liter. I think that's a good target. Depending on what feed source you have, you might not have any ammonia issues at all. If you're receiving a lot of proteins, you might have some pretty high ammonia concentrations. It just depends. It also depends on what you're doing on your dewatering program and where your centrate's going. So, that's all going to be something that depends on the process to process, but below 2,500. But I think another thing is you can be above 2,500. I've seen papers in the last 4 or 5 years that have shown digesters operating stably at 6,000, 7,000, 8,000. But the main key was you have to acclimate at those ammonia concentrations. So if you have high ammonia, try to maintain a stable level and try not to change it abruptly. Stability is key, and your biomass will acclimate to a certain point. But I think you're going to get better methane potential at the lower concentrations. All right, so now we're going to go to our next poll question.
All right, everybody, we've got a poll question here. What is the rate limiting step of digestion? So this is a single choice answer. Hydrolysis. Now, Erik, you're going to have to jump in and say these for me.
Yeah, hydrolysis, acetogenesis, acetogenesis, and methagenesis.
I appreciate that.
It
would be comical, I'm sure.
Acetogenesis and acetogenesis are so similar that I think everybody just gave up on it and just called it the acid phase. But
I've heard of that.
Yeah. So for those of you who are curious, actually, generally when you talk about acid methane split phase digestion, your hydrolysis and your aceto with a D genesis are going to be in your acid phase. And more often than not, your acetogenesis is going to be split between the two, and your methagenesis is going to happen in the methane phase, because as you move the acid phase into the methane phase tank, you're going to be carrying some unconverted acetogenesis, and you're going to have some acetobacter in your methane phase that are going to produce acetic acid in your methane phase, which is I don't know how many people are that knowledgeable about that, especially since it's not a common process.
We almost have 100 of you answering. Let's go, guys. 96. Can I get 4 more? Come on. Oh, yes. Thanks, everybody. All right, 102.
All right. So, and of course, the answer is hydrolysis. Now, if your biomass is suffering, you might have other rate limiting issues, but generally your hydrolysis step is going to be the rate limited step in digestion. And that's one of the reasons why you've seen so much innovation in the area of pre-hydrolyzing sludges and feedstocks into digesters. And that's another conversation for another day. but a lot of interesting things happening trying to reduce that rate limiting step. And in fact, I can tell you, we've worked on some projects in the thermally hydrolyzed sludge area where the digesters were able to get down to where the rate limiting step for the digestion process was the washout of the biomass from the digester. And that limited them to about an 8-day digestion framework. And, to me, the idea of the constraint on digestion being washout of your biomass, that's a pretty exciting concept as far as methane production and being able to handle all these additional waste streams with our existing infrastructure and capacity. So other important considerations: maintain proper mixing, maintain homogeneous digester volume for the biomass. If you're adding a bunch of co-digestion waste, and you want to have good mixing in your blend tanks to make sure that you're blending that properly before you're feeding it in, and you want to have good mixing in your digester to maintain homogeny, and make sure that if you do have rapidly hydrolyzing things that you're feeding in the digester, that you're distributing those volatile acids, that you're distributing pH, that you're distributing temperature, and keeping that as stable as possible. Because if you're not doing those things, you're going to get high concentration pockets that are going to create inhibition, and they're not just going to inhibit that area, but as they affect your biomass, that's going to cascade, and you're going to be reducing certain factors of your biomass and reducing your potential. So you really want to maintain a homogeneous digester and limit as much as you can any inhibition. You want to provide consistent pH and temperature. As we just discussed, you don't want to have pH spikes and swings in your digester. You want temperature to be stable. And then you want to provide direct mixing of the surface to prevent scum layer formation, especially if you're adding food waste. Anything that's being pulped or processed, anything that's being depackaged, food waste is going to have a higher potential for floatable constituents, cell walls that have a buoyancy, and also you're going to have fog that potentially can create scum on the surface. So you want to have direct surface integration from your mixing. There's a couple different ways to do that, and depending on what you're receiving, how bad that issue is for you. But definitely consider it, especially if you're building a new digester, or you're reconfiguring an existing digester to take on new feed constituency. This is all going to reduce your chance of indigestion and digester upset. So Rotamix mixing systems, just real quick. We provide Vaughan company manufactures and sells Rotamix mixing systems into the anaerobic digestion market, which is why I get to work for such a great company and talk about digestion all day. So our hydraulic mixing system uses fixed nozzles and an external Vaughan chopper pump. There's no moving parts in the tank. We have multi-zone mixing, which creates an even mixing flow across the diameter, even in very, very large tanks, 100-foot diameter plus, and all sorts of different geometries. We provide multiple discharge points, creates even distribution of solids, so we can put mixing down at the bottom. If you've got grit and other settlables that you're concerned about, we can have nozzles up near the surface to deal with scum and other things, all to maintain as stable a mixing and process as we can for you. We do computational fluid dynamics to model each mixing system we design, or at least inform it if it's a similar geometry or shape. And most dependable way to model a mixing system design performance before you build anything. So we definitely recommend looking at the fluid dynamics of your process and having a good understanding of the rheology that's going into that. Foam suppression. Foam buster evenly disperses droplets over the digester surface. This is one of our Rotamix nozzle with a splash plate that provides a dispersed droplet that can cover a very large surface area of the digester and maintain foam suppression. Helps control digester upsets, especially in the co-digestion arena. You're probably going to have issues with foaming every now and then, and having a proactive solution to that is going to definitely keep everybody at your plant happy, because nobody likes a foam upset, especially when it overtops. I've seen some horror stories and pictures of what can happen. Optional scum nozzle resuspends floatables and prevents stratification. So we provide a scum nozzle, which is a nozzle that doesn't necessarily directly contribute to the mixing, but just looks to re-entrain anything that's on the surface layer and provide constant liquid to that surface layer to keep it from drying out or caking or creating a scum layer. And I know some of you have probably had digesters that had really nasty scum blankets, and this can help prevent that. And if you have it, we can keep it from happening again. This is used with Rotamix, or we can provide as a supplemental system to an existing mixing or digester to prevent foam or scum buildups. So if you have an existing digester and you're not in a capital position to do a complete redesign of your digester, but you have some foaming issues and things you want to deal with, we can sell these as standalone systems for just foam suppression and other issues. So feel free to contact us at the contact info at the end if that's something you are interested in learning more about. So in conclusion, have a plan to ensure consistent organics receiving, provide flexibility to control feed rates to the digester. Data is your friend. Have good testing procedures. Know what you're receiving, know what you're putting in your digester. If you have to troubleshoot an issue, it's going to give you a much easier place to start. And it's going to allow you to be proactive rather than reactive in the management of your digester, which is always going to save money and improve your process. And maintain stable conditions of your digester. Make sure that your heat exchanger is sized appropriately for the temperatures that you're trying to maintain and the environment that you're operating in. Make sure that your pH is remaining stable. And if you have pH swings because of different feeds that you're putting in, make sure that you're augmenting that even before you feed it in to try to maintain alkalinity and pH in your digester. All these things are incredibly important. We got a contact page here. You can contact Vaughan for more information at chopperpumps.com. info@chopperpumps.com is the email. If you need a certificate for this webinar for your development hours, go ahead and send us an email at the email below, and we'll get that to you. I don't believe because of the varying requirements in different regions and between operators and engineers. If you need a certificate, please contact us. We'll send that to you. If you need specific information with respect to me as the presenter or any other info to fill out some sort of form to submit for your hour, please let us know and we'll help with that. It's just too difficult to individually go to each different region and state and get this pre-approved. It's much easier for us to work on a case-by-case basis, and we're happy to do that for you.
Yes, we are. We are extremely happy to do that. So any of those requests, please send to info@chopperpumps. As Erik stated, we do have a general certificate of completion for this. We can send you that link. It will auto-generate. You can print the PDF and have. But anything more specific, please send your request to info@chopperpumps. We have another poll. I wanted to present this poll. I'm very interested in seeing everybody. Hopefully, I would like to know, will you be attending WEFTech, and will Vaughan Company be seeing you there? Myself, Stephanie Vaughan, Erik Larson, Derek Vaughan, and a lot of our other Vaughan team will be there. I'm sorry we won't be seeing, looks like the majority of you guys, we won't be seeing you. Hopefully next year at WEF, maybe if you, as the days go by, we'll see you at some of those specialty conferences or other industry events that will be happening that, hopefully as things open up more for us. But definitely stop by and see us at booth 2021. It should be an easy one to remember. Booth number 2021, and come visit Erik, talk more about this, maybe your specific, you've had time to think about it, more in-depth questions, your process that you'd like to discuss, how Vaughan Company can help you. So looks like most of you joining us won't be in attendance, but like I said, we hope to see you soon. And then if you need any more information, info@chopperpumps.com is the address to find. We have a few questions here. We can go ahead and close that poll and move on. I'm just going to start from the top.
Yeah, go ahead.
All right. First one, it got swiped over. So any experience with adding coagulant chemicals like ferric sulfate to aid in co-digestion of organics?
So I don't have any specific experience with that. Generally, you're going to see that in the flocculation aids for prior to the thickening for thickened waste activated sludge to help with gravity belt thickeners or other process. I can't say I've seen any use in the digester itself. Generally, I think the digesters that we're working with are going to be continuously stirred tank reactors, and so a coagulant is potentially going to create a more challenging mixing environment. So I'm not sure that that's necessarily going to be. I see the next question, which is going to be, what's the best way to do inhibitive assay? There are standard procedures that are put out by the EPA and other regulatory bodies. I would look to those. It is a standardized test that is put out, that metrics are put out for. I would recommend looking to those and speaking with whoever's managing your lab data for their capabilities there.
All right, next question. What's a good ratio of fog to blended organic material?
I wouldn't say that there's necessarily a best ratio. You can digest just pure fog. But I think what really it comes down to is maintain an understanding of your digestion process, maintain an understanding of what it looks like when it's running well and stable. And if you're adding if you're starting to add fog or you're adding anything new to your digester, start slow and build up, and watch all of those metrics that you've set for what your digester looks like when it's operating well, and try to check to see if you're seeing any movement there. So if you're looking to, so let's say you're looking to start adding 1,000 pounds a day of fog into your digester. Don't just start at 1,000 pounds a day if you haven't ever added any in. Start at a slower rate and build up over time, and keep track of what's happening in digester pH. Let's say you're doing volatile acids and alkalinity, once a week or once every 2 weeks. Maybe start doing it 3 times a week if you're gonna make a change like that, and monitor that. It's something that you gotta figure out for your system. I wouldn't say that there's really a limit though. Like I said, you could digest pure fog if you wanted to, but it's going to be a lot more challenging because you're dealing with a single feed that is very very volatile.
All right, next question. We've got question, any guidelines for incoming TS versus internal digester TS to ensure proper distribution? Incoming too thick to blend properly with internal digester contents?
I think you don't really have an issue with blending until you get to cake. So if what you're adding is better described as cake rather than sludge, then you might have some trouble getting that to break down and distribute them in the digester. And I'm actually working on a project right now that's looking at how to manage that, because they are receiving cake into the digester for reasons that are very complicated. But I think the key is whatever you're putting into the digester, if you have good volatile solids destruction, your digester is probably going to be about half that concentration. So if you're feeding 6%, your digester is probably running at 3 to 3.5%. If you're feeding 8%, you're probably running about 4%. And I think that's a good rule of thumb. So whatever you think the capacity of your digester is from a total solid standpoint, based on whatever your mixing design is or what the digester was designed to handle, you can generally feed about double that if your digestion process is running efficiently. And I don't know if that answers the question quite how it was hoped, but that's a good rule of thumb. And I would say you can probably feed up to about 8 to 10% in a digester, but make sure that your digester can handle that 4 to 5% digested sludge in the digester itself, because that might be what really limits how thick you can feed into your digester. And I will say thermally hydrolyzed or chemically hydrolyzed sludges are going to have a much different rheology which is the study of the viscosity of the fluid or the factors of that, and you might be able to go much thicker than you would in a conventional unhydrolyzed sludge. So there's a lot of factors there.
All right, next question. Scum nozzles for large wet wells would be useful. What's the model name that they go under?
So we have, so for wet wells, we have vertical recirculators, which can definitely be used for mixing pits and are kind of like an all-in-one mix and transfer. For larger receiving wet wells, we can do standalone Rotamix systems that provide mixing for scum or other issues. It really just depends on the size. I would say once you start getting above 20,000 gallons, you start getting into the area of a standalone system, and below that, there's a lot of other options. We have our vertical recirculators, and then we also, or submersible recirculators, and then we also have conditioning pumps that can be placed in, and those are a great solution for wet wells that maybe have difficult access or can't be taken offline easily. Both. I think that physical methods like our foam buster are definitely the way to go, but there are chemical defoamers out there, and I don't think there's anything wrong, especially if you have a history of really bad foaming issues, with having those chemicals on hand in case of emergency. But again, that's something that I can't say that I'm very knowledgeable about chemical defoaming agents and their capacity and applications. So that would be something that I would talk to your chemical supplier or a chemical engineer about, who has a little bit more knowledge about chemical defoamants. But for physical, I think that is a great proactive measure, even if you're not having an active foaming event, to just maintain a very low foam level and maintain a good surface layer in your digester. Because ultimately, if you don't have a good surface layer in your digester, you're not going to be able to off gas your methane, which is going to create a lot of problems.
Next question. We run 80% poultry manure and 20% fruit pulp digester. How can we reduce pH levels?
So poultry manure is a little bit different than steer manure, which is probably your issue. Poultry manure tends to be a lot more acidic. I would try to find something that's got a lot of alkalinity that you can source cheaply, and try to look at adding that. And worst case, you can just augment with additional alkalinity through bicarb or silage too. But silage depending on silage can help, but it can also create it depends. But I would say look for something that can add alkalinity and add that into your feed system. Because purchasing alkalinity in chemical form is going to be really expensive over time.
Okay, I'm going to jump over. I see there is a question in the chat box. You guys. All right, I'm going to, it moved. Let me pull it back up really quick. Okay, in the stages of hydrolysis and acetogenesis, are you actively adding the acidic catalyst to break down molecules, or is it simply an extension of the feedstock added to the organisms within breaking down the molecules?
I just saw a comment, and actually, yeah, sorry, my bad. Poultry waste is actually going to be really high in ammonia and be very high in pH. I got myself mixed up in my head because of the framing of the question. So I'm going to need a little bit more clarity then on whether the issue with the poultry waste was the pH is too high, or what, or if the fruit pulp is just so acidic that even with the chicken manure, you're not seeing that balance. And then at that point, you might be just in a situation where you have to add chemical alkalinity. So thank you, whoever called me out on that. You're absolutely right. That's my bad.
Do you want me to reread that?
Yeah.
Okay.
Please.
Okay. I even did my pronouncing of the word perfectly. In the stages of hydrolysis and acetogenesis, are you actively adding the acidic catalyst to break down molecules, or is it simply an extension of the feedstock added and the organisms within breaking down the molecules?
Yeah, so that's going to be completely your biomass. So you're going to have a mix of aceto and acetogens that are breaking down. Once they're going to be attacking those monomers and those larger molecules and breaking them down into a form that they can then feed on and produce those volatile acids, and that's their metabolic pathway. And then you're going to have other bacteria that are taking those organic acids and converting them to acetic acid, and that's their metabolic pathway. And so that's where you get the aceto and the acetogenesis. There's no catalyst or other thing that you need to add into the digester yourself. That's going to all be provided by the biomass and as part of how they break down those organic solids. There's definitely things out there that can help them. So for example, like cellulose, you can add a cellulase enzyme to break down cellulose to make it easier for those bacteria to attack it, because naturally they'll produce very low concentrations of cellulase protein or enzyme. But you're kind of getting into things that are more industrial chemical manufacturing and not organics management from a wastewater standpoint at that point.
Okay, next question. Should blend tanks be reheated prior to feeding into the operating digester?
Not necessarily. It depends on where you live. If it's really cold and you're going to, and you want to preheat, both to maintain pumpability and to not add a bunch of cold sludge to the digester, I mean, that might be a reason why to do it. If you've got fog and you're trying to keep it from solidifying, if you've got unhydrolyzed or what's the word? If you've got fog that has a potential to solidify, you might provide heating there as well. But outside of that, no, there's really no need to heat a blend tank.
Okay, with that, we have taken all the questions. Thank you guys for participating today. We really appreciate your time. I know that you guys are all very busy, so taking your time to join us, Erik, Larson, and Steve Macomber, thank you. You can watch this webinar again. Give us about till the end of the week, maybe Monday next week, and we will have this downloaded and then up and running on our website on the Vaughan education page. You can find our past webinars. This is, I believe, the 5th in the series of the webinar topic, Rotamix webinar topic. And then we've got a couple other in there about wipes wreaking havoc on collection systems. If you guys need more information or are looking for those certificates, please send an email to info@chopperpumps.com and we will get back to you as soon as possible. I don't know if Erik, you have any closing things you'd like to add?
No, just thank you so much for joining us. This is always a great time to do these, and I appreciate everybody participating.
All right, Steve Macomber, you've got anything from way out in North Carolina you'd like to add as we close out here?
I'll just add that was great. I enjoyed it after all the technical details. We appreciate it. We have the experience. Please lean on us if you have any questions about a project, and happy to support your efforts.
All right. Thank you, everybody.